So what I would like you to do is I want to have on one side of whatever table that you're using, make sure that you have your graph with you, and on the other side, okay, make sure that you have this page with you, okay, because we're going to be looking at this page today lah. Okay, so in our previous experiment, okay, what we did was we measured the angle of the incident ray and the angle of the diffracted ray. Sorry, refracted ray. Okay, because it's the refraction experiment lah. Okay, and we find that every time the light moves from air to a more dense, optically dense material, okay, like for example glass, okay, we find that the light ray will bend nearer towards the normal. So the R is always going to be smaller than the I if it is moving from a less optically dense to a more optically dense. And it's going to be terbalik for the other way lah. Okay, so that's our basic premise for the beginning of this. Take a look at your graph. Okay, and let's start with the conclusion. Okay, what is the conclusion for this experiment? Can anybody tell me how do we write the conclusion? The conclusion has something to do with the aim. The aim of the experiment is to determine the sorry, what's the aim of the experiment? To determine the relationship, bukan? To investigate the relationship between the incident angle and the refracted angle. So can anybody tell me what is the conclusion for this experiment?
The bigger the angle of incident, the bigger the angle of reflection. Therefore, the hypothesis is accepted.
Now we're going to come to this graph, and this is where I need you to look at your graph lah. Okay, so look at your graph and calculate the gradient. Okay, do you know how to calculate the gradient? Remember? Okay, I think you learned this in AdMaths. Huh? So choose 2 points lah. Any 2 points you want, you can choose this and this. Okay, draw the triangle. Okay, and then after that, state the coordinates, and then the gradient will be y2 minus y1 over x2 minus x1. Okay, so I'm going to give you 10 minutes. I'm going to give you 5 minutes. It's too long. 10 minutes is too long to calculate gradient. I'm going to give you 5 minutes to calculate the gradient. And then after that, I want you to put the value of your gradient into our Telegram group. Okay, so just write down how much is your gradient. M equals to how much? M equals to how much? Two decimal places enough. Okay, give your answer in 2 decimal places. Okay, 5 minutes. In 5 minutes, I want to see all the values of the gradient. Okay, now just type in your answer. Okay, continue to type in your answer if you have. But according to this one, okay, according to my sample here, it's about 1.52 lah. Okay, glass, actually the value for the gradient is about 1.5 to 1.54. Of course, depending on what kind of material you use now. Okay, but I think if you're around that area, it's fine. So, if you notice this graph, okay, the y-axis, okay, the y-axis of this graph, okay, represents sine I, and the y-axis. And the x-axis of this graph, the values that you calculate here, is the values of sine R. Okay, so this is a very important thing. Why do we do this graph? Because we use this graph to calculate the gradient. And since the gradient is equals to sine I divided by sine R, and we have learned previously that sine I divided by sine R is the formula to calculate the refractive index of the material. Okay, so this is the one, write an equation for the refractive index. It is n equals to sine I over sine R. Okay, and I want you to make a short note over here lah. Okay, the gradient of the sine I against sine R graph, okay, equals to the refractive index. Okay, so if you remember from Monday's class, I said that there are 4 ways to determine the value of n. Okay, one is by this formula, n equals to sine I over sine R. That's the first way. The second way is this one. Use the speed of light in air and the speed of light in medium. Okay, that is the second way. The third way, okay, is to calculate the gradient of the sine I against sine R graph, which you already did lah. When you calculated this gradient, actually you are calculating the refractive index of the glass block that you use in the experiment. Okay, so please write this down. It's a very important thing. Okay, we use this method in experiment. Okay, when you're doing an experiment and the experiment say, okay, determine the refractive index, we don't use this formula. We use the gradient of the graph. Okay, that's why you have to plot the gradient of the graph. Okay, is that okay, everyone? Yeah, so only Ari and possibly Rahman. But Rahman, you need to change the graph, right? So we see lah. Okay, all right. So let me continue. Hold on, let me continue from here. Okay, now we're going to look at another aspect to refraction, which is called real depth and apparent depth. Okay, real depth is dalam nyata, yang sebenar. Okay, the actual depth lah. You know what is depth? Depth is kedalaman. Apparent depth, okay, is what is apparent to your eye. Apa yang kamu nampak. Okay, what you see. Okay, or expectation lah, fine lah. If you want to call this, you can call this expectation versus reality. So apparent depth is the expectation. When you see, then you see, oh, okay. But the real one is the reality. Okay, the reality is this. So for example, the mother is observing the legs of her son in the pool. If you look at the legs of the son over here, it looks much shorter than normal, bahkan. His legs appear to be shorter because of the refraction of light. So this is one of the uses, well, one of the applications of light refraction. It makes things in the pool look more shallow than it seems. And I can tell you, there have been many people who have been fooled by what they saw in the pool. You know, they look at the pool and then they say, "Oh, very shallow ni, jom." Okay, then they lompat inside lah. And then after they jump inside, what happens? They realize that the water is up to here. It's much, much deeper than they thought it was. Okay, and this is because of the refraction of light. Okay, the swimming pool looks shallower than it is normal. Okay, that's why that's why most of the time, you know, the like the Olympic swimming pools, right? Usually it would be an indoor one. Okay. I have heard this being said before, and I'm not really sure whether this is true, but they say that it is indoor so that, you know, it kind of reduces the effect of refraction, so that they actually don't get fooled by the depth of the pool itself lah. Okay, another one is that the coin appears closer to the surface of the water. Okay, let's take a look at this. So let's say you put a coin over here in a cup. Okay, in a cup that you cannot see. Okay, so say for example, this is the cup. Okay, and then, sorry, this is the cup. Okay, and pretend that this cup is like you can't see anything. Okay, then I put a coin inside. Okay, I put a coin inside, and then I angle my eye. Okay, I angle my eye in such a way that I cannot see the coin. Okay, don't like this, or like this, you can see the coin. But you know, like this, like at a certain angle, you can't see the coin anymore. Okay, then after that, what you do is you pour in water until it's full, you know. Okay, and now what you will see is that suddenly you can see the coin. You didn't change your position of the eye. You didn't move the cup nearer to you. Or no, you put your eye at a position where you cannot see the coin at first. But when you pour in water, you find that suddenly you can already see the coin. Okay, not because the coin floated to the top. Okay, the coin is still at the bottom. Okay, but it just looks shallower than it seems. You need to try this at home. Okay, but this is what happens. Okay, why is it that you can see the coin, and we call this a virtual image? Okay, we call this a virtual image. So why is it that you can see? It's because of this. The position of the image of the coin. Sorry, this is activity 2 in page 172. Okay, the position of the image of the coin appears to be nearer to the surface of the water. It's nearer to the top over here. At first, there's no water lah. Okay, then when you pour in water, it seems that the coin is here instead of here. Okay, nampak kepada kita, it looks to us only. It's actually still down there, but it looks to us as if it is here. Why? Because light travels from water to air, okay, and because it is traveling from water to air, this is this is more optically dense to less optically dense. Okay, and remember, if it is traveling from more optically dense to less optically dense, it will be refracted away from the normal. Okay, so that this is what happens. Okay, astaga. Sorry. So over here, let's say I draw a normal line over here. Okay, as it comes, so this is the I, and this is the R. Okay, so it will be refracted away from the normal towards our eye lah. Okay, let's say kita punya mata di sini. So, but the problem is our eyes, okay, mata kita can only interpret light traveling in a straight line. Okay, our eyes cannot understand that light can be bent. Okay, so whatever light that comes to us actually comes to us in a straight line. Okay, we cannot understand, we cannot comprehend that, oh, light can bend. So to us, it looks like light travels in a straight line. So when we see the refracted ray, okay, and if we extend it to the back over here, okay, this is where we will see the coin. Okay, that's why people's legs look shallower than normal. If you see the fish inside the pool, the fish looks like it's actually higher, nearer to the surface of the water, but actually it's much deeper inside. Okay, because the light from the fish that comes to our eye is refracted away from the normal. Okay, and when it is refracted away from the normal, it will make the picture of the fish or the coin look higher than normal. Okay, because of the refraction is away from the normal. So this is what I want you to do for this one. Okay, for today. Okay, this is the first assignment lah. I want you to carry out this refraction activity. So you take a cup. Okay, preferably not a cup that you can see through lah. Take a cup that you cannot see through. Okay, you take a video of this lah, or ask somebody to take a video. Take a video of your viewpoint. Okay, take a video of your viewpoint. So you angle the video in such a way that you cannot see the coin at first. And then you pour in the water. Okay, you pour in the water and then you look at the video. Okay, after you pour in the water, after a while, okay, then you should be able to see the image of the coin. Okay, so this is the activity that I want you to do. Take a video of it, okay, and then explain this phenomenon in your own words. Okay, try to not just read from this lah. Okay, try to explain this using your own words. Okay, see whether you understand what you are explaining. Okay, if you just read like this, I might as well ask a standard 2 boy to read this for me lah. Okay, don't read. Okay, understand what is happening and try to explain it using your own words. Okay, and then after that, in the same video, okay, state 2 other situations which is similar to this phenomenon, refraction of light. Okay, we will discuss this in a little while, but actually I've already shown you 2 lah. Okay, about the pool and everything. But there are many others. You can research it on the internet. Just state, don't need to explain. Okay, so just state, oh, the 2 other situations that is similar to this is when this one, and also when this one. Okay, then you upload your video, and I'm going to give you maximum 2 minutes only. I don't think you need more than 2 minutes to carry out the activity and then explain. Okay, upload your video into the Flipgrid, which I will also share the link with you all later lah. Okay, the reason why I want you to do this assignment is I want you to see for yourself. Okay, and because if I just talk, after you finish this class and everything, you forget. So you do it. Okay, you do it using your own eyes and your own cup and your own coin. Okay, if you don't have a coin, which is who doesn't have coins, right? Okay, if you don't have a coin, make sure you choose something that is heavy, that can sink to the bottom, that is flat. Okay, maybe like a key lah. I think a key also can. Okay, yeah, a key is can. Don't use a safety pin, please don't, because safety pin will float. Okay, you put the water in, instead of seeing the image of the safety pin, you actually see the safety pin. Okay, make sure that it sinks to the bottom and it will stay there even after you pour in the water. Coin is the best. Try not to use an object that is round or big, like a stone. I know stone is heavy, unless you have a flat stone. Flat stone can, but don't use this, the huge stone, because it will look like a ball. A little bit more difficult. Difficult for you to find the angle where you can't see the ball anymore. Okay, so use a coin, use a key, something heavy that will sink, and then yeah, okay, do your video. I will give the deadline for this a little bit later. I will tell you later, but let's see how far we can go today. Okay, so let's talk about real depth and apparent depth. Okay, so the refraction of light gives us a false impression of depth. Okay, because of refraction, okay, we don't really see how deep the pool is. We don't really know that the coin is actually at the bottom. So the water or the fish in a deep pool appears less deep than it really is. Okay, it looks to us, bagi kita kan, we see the fish here, but actually it is here. Wow, magic. Okay, so we call this situation real depth and apparent depth. Okay, so let's consider this lah. Let's say you have this object O, similar to the video assignment that I'm asking you to do. So you have this object O, and there's this height over here. Okay, so straight directly lah. But if it is bent like this, let's say the light travels from here to here at a certain angle, okay, we know that it's going to be refracted. Okay, so this one is going to be refracted, this one is going to be refracted, this one is just going to go straight. Okay, which is what happens over here. But since this one has an angle to it, so we know that it is going to be refracted away from normal. Okay, it's going to be refracted away from normal. Why? Because it is going from more optically dense to less optically dense. Okay, less optically dense. More optically dense to less optically dense will be away from normal. Okay, MLA, more less away. Okay, more less away. So remember that. So on the right hand side also the same. It will be away from normal. Okay, but if we put our eyes here, okay, or if we put our eyes here, oh no, sorry. Okay, if we put our eyes here, to us, the light travels in a straight line. We cannot see this one. What we think that we are seeing is actually this one traveling in a straight line. Okay, and so these two, if we look from here or here, we see that the coin or the object over here, okay, this is what we see. This is the reality. Okay, the image is what we see, and this is the actual one. So the depth, the kedalaman from the object to the surface, okay, is what we call real depth. This is the real depth. Okay, the distance from the image, what we see, to the surface of the water is the apparent depth. Okay, this is actually what we are seeing lah. Okay, I'm going to give you some time to copy this into your this one, and then mark and label the real depth H big. Okay, so this is big H. Okay, real depth is big H, apparent depth is small h. Okay, yeah, mark and label first. I will give you the definition in a little while. Okay, so you need to draw all these light ray diagrams. This is the normal line, remember? Okay, this is the normal line. Okay, remember that this refraction is away, okay, away from normal, because it's going from more dense to less dense. Okay, more optically dense to less optically dense. Okay, I'll give you 2 minutes to copy this. All right, let me carry on now. Actually, the next slide also shows the same drawing, so I'm going to just leave this here. Just remember that the real depth is the big H, and the apparent depth is the small h. Okay, so what is the definition for the real depth? The real depth is the distance between the water surface and the object. Okay, I think this is the important thing. Everybody needs to remember this. That when we're talking about depth, kedalaman diukur. Okay, depth is measured from the water surface, not from the base. Okay, not from the base. Okay, so remember in the previous class, I said that, and also today, I said that there are 4 ways to count the refractive index. So the first way is n equals to sine I over sine r. The second way is n equals to the speed of light in the vacuum, or in this one, over the speed of light in medium. Okay, the third way is the gradient. Okay, if you calculate the gradient of the sine I against the sine r graph, okay, then you calculate the n also. Now this is the fourth way. The fourth way is n equals to the real depth divided by the apparent depth. Okay, this is the fourth way. So you need to know all the 4 ways lah. Okay, so the equation for the refractive index, which involves real depth and apparent depth, is n equals to h over h. You want to count the refractive index of water, for example. Okay, so this brings us to another experiment for today. But this experiment, unfortunately, I don't have a apa itu? I don't have a simulation for it lah. Okay, so we're just gonna have to this one. Hopefully, when you come back, we may be able to do this. But actually, this is one of the most difficult experiments to do, not because it is complicated lah, but it's very difficult to see the image, okay, of the apparent depth. Okay, so this experiment, you can copy this down if you want. So the inference is the position of the image, or the real depth, is influences the apparent depth. Okay, or you can also say, since we want to say depends on, right? So we say apparent depth. Okay, apparent depth depends on, okay, real depth. Okay, also can. But this lah, the hypothesis will be the greater the real depth, the greater the apparent depth. Okay, the aim of this experiment, this is in page 238 in your textbook, to investigate the relationship between big H and small h. So the real depth, apparent depth is the manipulated and the responding variable, and the fixed variable is the density of the liquid. Okay, let me give you 1 minute to copy this, then I'm going to go to the next one. Okay, so this is how the experiment is like lah. Okay, it's a tough experiment because there is one component that is missing, which is this beaker. Okay, we have a 1000 ml beaker. Okay, but the problem with this is that the beaker actually needs to be a straight beaker, like an aquarium lah. If this was an aquarium, this would be much easily done. But all our beakers in the lab are round like this, so it's very difficult to do. But the idea is this: we put this pin down here in P1, okay, and then after that we look from the top. So we stick a pin PO here with cellophane tape to the base of the beaker over here. Then we fill the beaker with water to a depth of 6 cm. So this 6 cm, okay, is the real depth. Okay, this depth is the real depth H. Okay, then we observe the image from here, above the water surface. So you have to look from the top lah. Okay, you look from the top and see. Then now what you do is you adjust this position, PI. Okay, you adjust this PI pin. Okay, means you move this either upwards or downwards. Okay, until it appears in the same line as this one, okay, as PO. Then you measure the distance y between PI and the base of this one. You measure this distance y over here. Okay, you measure this distance y. And then you can calculate the apparent depth. So if let's say the real depth is 6 cm, and then this y that we get, since the y we measure from the ruler, right? Let's say the y is 2 cm. So my question to you is, how much is the apparent depth? The real depth is HCM. How much is my apparent depth? Anybody? Is it 2 cm? Okay, it will be 4 cm, because remember, depth is calculated from the surface of the water, not from the bottom of the beaker. Okay, but because our ruler is adjusted this way, so we have to calculate from the base lah. Okay, so yeah. Okay, so this is the apparent depth. And then you repeat this experiment with real depth of H7, 8, 9, 10. So you change the height of the water. And the hypothesis of this experiment says that if you change the height of the water, the apparent depth also will become bigger. Okay? And so this is the reading, okay, for the values of y and h. So what I want you to do is, I want you to copy down this, okay, and then, sorry, another graph paper. Okay, so this is your second assignment for the day. Number 1, draw the graph. Okay, number 2, calculate the gradient. Okay, and then number 3, state the refractive index of the water. Okay, draw the graph, calculate the gradient, state the refractive index, just like you did in the Telegram group. Okay, so you just write, after you calculate the gradient, because we already say the gradient equals to the refractive index, even if it is h over h. Okay, because the graph, what is this graph that we want to draw? Okay, graph of real depth against apparent depth, big H over small h. Okay, so the refractive index, n equals to tau. Okay, how much is it? Put all this in your graph paper and then upload. Okay, upload into the Padlet just like yesterday's graph. Okay, and but this one, remember, I want to see the calculation for your gradient. I want to see how much is the value of the n that you got based on this reading. Okay, so I can't do this experiment, so I can only give you the reading. Okay, so you calculate the apparent, sorry, you just use this data and this data, okay, and draw the graph. Okay, and then reminder to Meryl and Joey lah. Remember, your graph must start from 0, 0. Okay, must always have an intercept at 0 lah. Okay, is everybody clear about this assignment? Yeah, there are 2 assignments today, but this one, before you come for Friday's class, this one, the one that I'm showing you now, this is the one that must be done. The video, I will give you some time to do the video, but this one is the one that must be done first. Okay, is everybody clear with the assignment? If you're confused? Okay, all right, thank you. So let me conclude by just taking a look at the last 2. Okay, take a look at this number 3. No, number 4. Oh no, I'm missing my number 3. Oh, yeah, sorry. This is number 3 inside of this one. Why the man's legs stand inside the water appear to be shorter? Okay, again, the same explanation. Light travels from the feet in the water, which is denser, to air, which is less dense. More dense to less dense. The light is refracted away from the normal line. Okay, so the explanation is always the same. Go from water to air, the light refracts away from the normal line, and that's why the man's legs look shorter to us. Okay, because dia terpesong keluar. Okay, it is refracted away from the normal line. So there are two questions there lah. The first is, a man tries to shoot a fish as seen by him in the water. Okay, but his shooting does not hit the fish. He sees the fish over here actually. Okay, but he shoots here lah. But actually dia tidak kena. So why does his shooting fail to hit the fish? Okay, so when we look at this explanation, we know why lah. Because it hits the image of the fish, which is above the real fish. Okay, this is why. Okay, he fails to hit the actual fish because he's actually shooting at the image of the fish, which he sees because of the apparent depth. Okay, which he sees because of the refraction of ray. Okay, so if you are the shooter lah, like, and this one I always see, like, last time in the old days, how people will catch fish is they will spear or tombak. Okay, or they can use a bow and arrow also lah. Okay, so if you are catching the fish, right, and then you see the fish in the water, okay, and you know that the image that you're seeing is not where the fish actually is. So how should you adjust? How should you adjust if you actually want to hit the fish? Anybody want to suggest? It's not very logical one. Where is the fish actually? Is it higher or lower than what you're seeing? It's actually lower bahkan. So you know that, so your eyes are so this is why our eyes are very bad. Our eyes actually lie to us. What we see is actually not there. It's actually lower. So how should you aim your gun or your spear? Should you be aiming higher or aiming lower? Shoot in front of the fish. Shoot a bit in front of the image. Okay. I think you kind of get what you are supposed to do lah. The most important thing is you shouldn't be aiming at the fish. You should be aiming away from the fish a little bit. Okay, and how we will write this is to hit below. Okay, I think I understand what you mean by in front. Okay, in front means is nearer to you lah. But what I mean is, so when you aim, so originally you aim this way, right? Okay, let's say you aim this way, you should aim a little bit lower. Okay, so you hit below or perpendicular to the fish. Okay, this is the important one lah. Okay, all right. So that's it for today. We will conclude this subtopic on Friday. Yeah.